Hello and welcome. Introduction. In this video, I'm going to show you how to use the TM4C123 general purpose timer to blink an LED. Now here is the block diagram of the TM4C123GH6PM microcontroller. And here we focus on the general purpose timer module. General purpose timer module, or GPTM. Now here is a table, table 11-1, taken from the TiVar TM4C123PM microcontroller datasheet, and it can be found on page 706. Now, from the table, we can see that each general purpose timer module, or GPTM, consists of 6. All right, 6 of these 16/32-bit timer, and they are known as timer 0, timer 1, timer 2, timer 3, timer 4, timer 5. And each of these timer is divided into timer A and timer B. Now, there are also 6 32/64-bit wide timer, and as before, there is the timer 0, timer 1, timer 2, timer 3, timer 4, and timer 5. Now each timer, as before, is divided into timer A and timer B, and these timers can be combined to form a 64-bit timer. Now here is the typical GPTM module block diagram. And as mentioned earlier, each timer can be divided into timer A and timer B. And as you notice, there are a list of registers here. What I would like you to do at this moment in time is to just have a glance of these names of these registers, because we will be discussing in detail some of these timers. For example, we'll be looking at GPTM CTL, GPTM RIS. Over here we have GPTM TAMR and GPTM TAILR, and so on. So just take note of this register's name, because later on I'll be referring to them in the video. Operating modes. The TM4C123 timer can operate in the following modes: one-shot timer mode, periodic timer mode, real-time clock timer mode, input edge count mode, input edge time mode, and PWM mode. Now in this video, we will focus on the periodic timer mode. Programming the TM4C123GH6PM timer. Now, before I carry on, I would like to acknowledge that I will be referring to the TiVar TM4C123GH6PM microcontroller datasheet a lot in this video. Now, you can download the datasheet from the Texas Instruments website. Please refer to the link in the description. Now, to program the timer, I will refer to page 722 of the TM4C123 datasheet. Now, there is a section that explains how to initialize and configure the timer. Now, what I've shown here is not the complete story. You really need to get hold of the datasheet and refer to it. Now, as mentioned a few moments ago, this video will focus on the periodic mode. And here are the steps, or some of the steps to initialize and configure the timer. Now, I will summarize the steps here. So the steps to program timer 0. So this is a summary. So step 1, enable the timer 0 clock. I'm using timer 0, so that's why it's timer 0. Disable, second step, disable timer 0. Third step, load the GPTM configuration register with a value of hexa 0, 0, 0, 0, 0, 0, 0, 0. And then step 4, configure the TNMR field in the GPTM timer N mode register, and then set the count direction. So the two things here, set this field and set the count direction. And then step 5, load the timer start value. And step 6, enable timer 0. Here we disable it. In step 2, in step 6, we enable the timer. And then step 7, we poll. That means we check the GPTM RIS register. Remember we mentioned this register earlier. And then clear the status flag in this register. The program. At this point of the video, I'm going to show you the complete program, and I will go into the details of the program later in the video. Now, the program is written in C. That is because I find it easier to explain how the TM4C123 timer works using C. However, I will show you how to program the timer using assembly language in a later video. So here is the main part of the program. And here are the functions, and this is the init GPIO function, and this is the init timer function. And then lastly, this is the toggle LED function. Details of the program. Okay, so let's start from the top. So this is the header file. So you need to use the include directive to include this header file. Then we declare the 3 functions that we'll be using in this program. The first function is init GPIO, init timer, and then toggle LEDs. So we declare the 3 functions used here. And then when we come to the main part of the function, we initialize the GPIO using the init GPIO function. Then we initialize the timer using the init timer function. And then in the while loop here, we toggle the LED using this function here. The init GPIO function. So this is the function here, basically the purpose of this function is to initialize the general purpose input-output or GPIO of the TM4C123. Now I have a video, which is this video, that explains the details of the TM4C123 GPIO in more detail. Please refer to the video, and I've provided the link in the description. Alright, so here is part of the schematic of port F of the TM4C series 123 G Launchpad board. And as you can see from the schematic here, PF1, which is port F bit 1, is connected to LED underscore R, which is the red LED, and LED underscore B, which is the blue LED, that's connected to PF2, that's port F bit 2, and port F bit 3, PF3, that's connected to LED underscore G, that's the green LED. And this schematic or partial schematic is taken from the TM4C series TM4C123G Launchpad Evaluation Board user guide, and you can find this in the appendix. Now let's take a closer look at this function. So this is the instruction here. Basically, this instruction enables the clock to the GPIO F, that is GPIO port F. Alright, so it will enable the clock for port F. And this SYSCTL is a pointer to a structure, and RCGC GPIO is a member of that structure. Now this is the general purpose input-output run mode clock gating control. That is the RCGC GPIO. RCGC GPIO. So this is the register, and we are interested in bit 5 here. So basically this register provides the software the capability to enable and disable GPIO modules in run mode. When enabled, a module is provided a clock, and access to the module registers are allowed. So basically this instruction here will set bit 5 to a 1. Now if you translate this binary into hexa, that would be 20 hexa. Hence this instruction SYSCTL arrow operator RCGC GPIO pipe equals 20 hexa, and 20 hexa is translated into binary because we want to enable bit 5, and that will enable the clock for GPIO port F. Okay, so this instruction here disables the alternate function of the GPIO, and GPIO F, right, is a pointer to a structure, and AFSEL is a member of that structure. The arrow operator is used to access the member AFSEL of the structure that the GPIO F points to. So this is the GPIO AFSEL register, and it is the mode control select register. Now, if a bit is clear, that particular pin is used as a GPIO and is controlled by the GPIO registers. Now, in this case, we are setting all the bits in the AFSEL to zeros. That means we clear all the bits, and that means all the pins on the is used as GPIO. Okay, so the next instruction, which is this instruction here, and this instruction sets the direction of the GPIO port F, in particular PF2 as output. So we're setting PF2 in particular as output. Now, GPIO-F is a pointer, and DIR is a member of a structure. Sorry, let me repeat. GPIO-F is a pointer to a structure, and DIR is a member of that structure. The arrow operator basically is used to access the DIR member of the structure that the GPIO-F points to. So this is the GPIO direction register, or GPIO DIR, and these are the bits that we are interested in. So basically, setting a bit to a 1, that configure that bit to be an output. So in this case, if we look at the binary, so they translate this binary to hexa, that is 04. Hence, we have 04 in the instruction. That basically set this bit as output to output mode. This instruction basically will enable the GPIO port F, in particularly the PF2, which is this bit here, will enable the digital function of that bit. The GPIO digital enable register, or the GPIO DEN register. All right, to use the pin, especially this one of interest to us, to use the pin as a digital input or output, the corresponding pin must be set. Like mentioned a few moments ago, we are interested in this bit, so this bit is set, all right, for digital function. In fact, this is the output. All right, so if we translate this binary pattern to hexa, it would be hexa 04. Hence, 04, hexa 04 is assigned to this DN register. The init timer function. So here is the code for the init timer function. And I'm going to go through each of these instructions with reference to the TM4C datasheet. So here are the steps to program timer 0. And step 1 is to enable the timer 0 clock. So this instruction here basically will enable the clock for timer 0. Now here is the general purpose timer run mode clock Reciprocating Control Register, or RCGC timer. Now we need to set bit 0, which is this bit here, to a 1 to enable the clock, hence this expression here. Alright, and from the datasheet we read a value of 1 enable and provides a clock to the 16/32-bit general purpose timer module 0 in run mode. Step 2. Step 2 is to disable timer 0. So this is the GPTM control register, or GPTM stands for General Purpose Timer Module, or GPTM-CTL. So we need to clear bit 0 to disable the timer. Now bit 0 has a label TAEN, and from the datasheet, this we know that a value 0 would disable the timer, and this instruction here will do that. Alright, so this instruction will basically set this bit or clear this bit to 0, thereby disabling the timer. Step 3. In step 3, we load the GPTM configuration register with a value of hex value of 0, 0, 0, 0, 0, 0, 0, 0 hexa. So this step is pretty straightforward. All we need to do is to load that hex value, this hex value, into the GPTM configuration register, or GPTM CFG. So all we need to do is to clear all these bits out, and this instruction here will do that. Step 4. So in step 4, we need to do two things. First is to configure the TNMR field in the GPTM timer and mode register. So we need to configure this field. And then second thing we need to do is to set the count direction. So here is the register TAMR. I think it stands for Timer A Mode Register, TAMR. With this, we need to take care of these two bits here, and this instruction here will do that. What does it do? Basically, it will set bit 0 and bit 1 to 1, 0, 1, 0, which is basically hexa 2. Alright, so from the datasheet, if we set this to hexa 2, that will set it to a periodic timer mode, which is the mode that we are interested in this video. And this instruction will do just that. So that is the first thing. Now the second thing we need to do is to set the count direction. And to do that, we need to clear bit 4, which is this bit here. So from the datasheet, we know that a 0 will set the timer to count down, and this instruction will do just that. We'll set this bit to 0. Step 5. We need to load the timer with a start value. So here is the register GPTM timer A interval load, or GPTM TAILR register. So this instruction here will load this value 00F42400 hexa, which is basically 16 million in decimal. It will load this value into the timer, and this would be the load value or the start value. Now let's take a look at how the load value is being derived. So we are going to assume the clock frequency, the system clock frequency, to be 16 megahertz. All right, and the design interval that we want, or I want, is 1 second interval. All right, which is basically 1 hertz. Now, to achieve a 1 second interval with 16 megahertz clock, the timer needs to count down from 16 million to 0. So the formula adopted for this case is TAILR equals desired interval multiplied by the clock frequency. So the desired interval is 1. So we put 1 here, multiplied by the clock frequency, 16 million. That will give us the 16 million. And if we convert this number, 16 million decimal, to hexa, you will get 00F42400 hexa. Step 6. Enable timer 0. Now this step is the opposite of step 2. Now in this step, we will enable timer 0. So this instruction here basically will enable timer 0 by setting this bit here, bit 0, to a 1. And from the datasheet description, we know that a 1, it says timer A is enabled and begins counting. All right, so we set this to a 1, and we use this instruction to set this bit to a 1. And finally, the toggle LED function. The toggle LED function basically implements step 7. Now in step 7, we poll or check the GPTM-RIS register, and it will clear the status flag of that register if necessary. And this is the toggle LED function. Let's look into the details of these instructions now. Okay, so this instruction here checks if the interrupt status bit 0 of the RIS register is set. Now, if that bit is set, then it will carry out these instructions. So let's take a closer look at this instruction. So this is the RIS register, or to be precise, the GPTM raw interrupt status register, or GPTM RIS. So this instruction here will check the interrupt bit 0, all right, of the register, which is this bit here. And this instruction basically, this part here of the instruction, the N, will perform a bitwise AND AND operation between the value of the RIS and this binary value, this value here. All right, basically what it does, it masks out all bits of the register except this LSB bit, which is bit 0, and then compare that bitwise operation result with this value here. So basically this is a compare, and if this bit of the RIS is set to a 1, all right, that means the timer has timed out. If this is set to a 1, then the comparison is true. Now we will examine this instruction. So this is the GPTM interrupt clear register, or GPTM ICR. So basically this instruction is used to clear, all right, bit 0, the LSB, bit 0 in the ICR or GPTM ICR register. All right, so it's as from the datasheet, we read, writing a 1 to this bit clears this bit here in the GPTM RIS register. Now this instruction here will toggle the LED. So this is the GPIO data register. So the values that are written to the GPIO data register are sent to the GPIO port pins. So in this example, this value here, all right, which is 04 hexa, in binary it is 0, 0, 0, 0, 0, 1, 0, 0. All right, so using this instruction, it will toggle this bit here. All right, so this operator here will toggle this bit here, all right, which is bit 2 of the register. Demonstration. Now for this demonstration, you will need the TIVA C series launchpad board connected to your desktop or your laptop. Okay, so we are here with the code that I've uploaded to the Kyle Microvision IDE. So let me just briefly go through it. So the file is here. The declaration of the functions used are here, and this is the main function, main C function, and here is the init GPIO function. Here is the init timer function, and then lastly but not least, this is the toggle LED function. All right, then I also have the my setup here. All right, let me expand. So my hardware setup. So this, my TIVA C series launchpad board is connected to the laptop. Let me put it here, and so let me go ahead and go to project and then do a build target, and I got no errors and no warnings. Now I download it to the board, and so we'll go to download, hit that, and it says verify OK So let me bring the video up. So what I need to do now is to press the reset button, and the blue LED is flashing. So it's blinking the LED. But if you notice the rate of blinking, or rate of flashing, it's a little bit faster than 1 second that I plan to have. Remember the calculation that we did? We said we want a 1 second interval, but this is faster than 1 second interval. So let's check it out with a logic analyzer, the outputs. Okay, so this is my logic analyzer, and what I'm going to do is I'm going to hook up this logic analyzer to the TM4C series launchpad board, and we'll look at the output with this logic analyzer. Okay, so I've got the logic analyzer, this logic analyzer here, connected to my TM4C series launchpad board, and I've connected the green color cable, that's the or jumper, that's the ground, and the yellow jumper, that's the output of port F bit 4. Alright, the yellow jumper is the output, PF4, and then the green is the ground of the board. Alright, so we can now turn to the software of the logic analyzer and look at the output. So this is the output from the logic analyzer. Let's measure the on state of this signal here. So let me just drag this across here, and it's measuring 320.05 milliseconds. Let me just zoom in. Alright, so it's 320.05 milliseconds. Let me zoom out. And let's measure the off state. It's also measuring 320.05 milliseconds. Let me zoom in again. Alright, so it's 320.05 milliseconds. Now, this is obviously way short of the 1 second that we calculated earlier. So what I want to do is to look into this, and then I would report back to you my findings and hopefully a solution to this problem. Hey, that's it for this video. Please join me in the next video, as I will be presenting the solution to the 1 second problem that we witnessed or we watched earlier. So thank you for watching, and I'll see you soon. Bye.